Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on vector space, lecture number 19, in which I will discuss on isomorphism of vector spaces. Now I define isomorphism of vector spaces. Let UF, F be the field, and VF be two vector spaces. A mapping F defined on U onto V is called an isomorphism of U onto V if number 1, F is 1, 1. Number 2, F is onto. Number 3, F A alpha plus B beta equal to A F alpha plus B F beta for all AB belong to F field and for all alpha beta belong to U. The third condition is condition for homomorphism or linear transformation. Under above conditions, U and V are said to be isomorphic, and symbolically we write UF is isomorphic. This is the symbol of isomorphic to vector space VF. The vector space VF is called isomorphic image of vector space UF. Therefore, isomorphism of U onto V is possible only when the mapping F defined on U onto V, F is 1, 1 onto, and F fulfills the properties of linear transformation. That is, F is homomorphism mapping. We prove a theorem. The theorem is isomorphism theorem for vector spaces. Now we state this statement. Two finite dimensional vector spaces over the same field are isomorphic if and only if they are of same dimension. Now we prove this theorem. Let UF, F be the field, and VF are two finite dimensional vector spaces over the same field F such that dimension of each of them be n. Now to prove that vector space UF is isomorphic to vector space VF, let S1 be the basis of UF, and S1 contains elements alpha 1, alpha 2, alpha n. Therefore, alpha 1, alpha 2, alpha n are linearly independent vectors, and any element of UF is expressed as linear combination of alpha 1, alpha 2, alpha n. Similarly, S2 be the basis of VF, which contains vectors beta 1, beta 2, beta n. Here number of elements in basis S1 be n and number of elements in basis S to be also n. Any vector alpha belongs to U is uniquely expressed as linear combination of vectors alpha 1, alpha 2, alpha n. This is number 1. Here A1, A2, dot 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 An are elements of field F. Let us define a mapping F defined on U into V, defined by function of alpha, means image of alpha, equal to this A1 beta 1 plus A2 beta 2 plus dot 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 An beta n. Since in the expression 1, here we see alpha is equal to a linear combination of alpha 1, alpha 2, dot 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 alpha n with unique scalars A1, A2, dot 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 An. Hence, mapping defined in 2 is well defined. That is, F alpha is an unique element of V. Now, to show F is 1, 1, the mapping F is 1, 1. Since A1 alpha 1 plus A2 alpha 2 plus dot 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 An alpha n and B1 alpha 1 B2 alpha 2 dot 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 plus dot 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 plus Bn alpha n are 2 elements of U, and let function of this element of U equal to function of this element of U. Since already we have defined into F A1 alpha 1 plus A2 alpha 2 plus dot 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 plus An alpha n equal to A1 beta 1 plus A2 beta 2 plus dot 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 An beta n. Similarly in right side. Implies that here A1 beta 1, here B1 beta 1. So, if we take this left side, we get A1 minus B1 common beta 1. Similarly, plus A2 minus B2 beta 2 plus dot 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 An minus Bn beta n. Since beta 1, beta 2 dot 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 beta n are vectors of basis S2. Therefore, beta 1, beta 2, beta n all are linearly independent vectors. Therefore, this gives A1 minus B1 equal to 0, A2 minus B2 equal to 0, dot 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 An minus Bn equal to 0. Implies that A1 equal to B1, A2 equal to B2, dot 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 An equal to Bn. That means A1 alpha 1 plus A2 alpha 2 plus dot dot An alpha n equal to B1 alpha 1 plus B2 alpha 2 plus dot 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 Bn. That is, if A1 alpha 1 plus A2 alpha 2 plus dot 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 An alpha n equal to F B1 alpha 1 plus B2 alpha 2 plus dot 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 Bn alpha n, implies that A1 alpha 1 plus A2 alpha 2 plus dot 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 plus An alpha n equal to B1 alpha 1 plus B2 alpha 2 plus dot 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 Bn alpha n. That means F is 1, 1 mapping. Now we shall show that F is onto. Since beta 1, beta 2, beta dot 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 beta n are elements of the basis of Vf. Therefore, A1 beta 1 plus A2 beta 2 plus dot 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 An beta n is any element of V. Means any element of V is expressed as linear combination of vectors of basis of V. Here, this is any element of V. Therefore, there exists an element A1 alpha 1 A2 alpha 2 plus dot 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 An alpha n of U such that function of A1 alpha 1 plus A2 alpha 2 plus dot 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 An alpha n equal to A1 beta 1 plus A2 beta 2 plus dot 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 An beta n. Therefore, for any element A1 beta 1 plus A2 beta 2 plus dot 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 plus An beta n, we get a pre-image in U. Therefore, F is onto. Now, we shall show that F is a linear transformation. Let A, B belong to F field and A1 alpha 1 plus A2 alpha 2 plus dot 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 An alpha n comma B1 alpha 1 plus B2 alpha 2 plus dot 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 Bn alpha n belong to U. Since any element of U is represented as linear combination of alpha 1 alpha 2 dot 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 alpha n, then function of A and this element plus B this element equal to, we multiply this and simplify, we get F A1 plus B1 alpha 1 plus dot 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 and so on. Since we know that function defined in 2, we get this value of this function is A1 plus B1 beta 1 plus A2 plus B2 beta 2 plus dot 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 An plus Bn beta n. We bifurcate this, we take common A and we get this element plus B common, we get this element. This element means function of A1 alpha 1 plus A2 alpha 2 plus dot 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 An alpha n plus B. This means function of B1 alpha 1 plus B2 alpha 2 plus dot 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 Bn alpha n. Therefore, we get that this equal to A outside function of this element plus B outside function of this element. Therefore, F is a linear transformation. Hence, F is 1 1 onto and F is a linear transformation. Therefore, F is an isomorphism of U onto V. Now, we prove conversely. Let UF and VF be two finite dimensional vector spaces such that UF is isomorphic to VF. Now, to prove that dimension of U equal to dimension of V, let dimension of U equal to n and let S1 is the basis of U. S1 contains vector alpha 1 alpha 2 dot 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 alpha n. Therefore, alpha 1 alpha 2 dot 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 alpha n are linearly independent vectors and any element of U is represented as linear combination of alpha 1 alpha 2 dot 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 alpha n. let F is a mapping defined on U into V, and this is isomorphic mapping. Let S prime contains elements function of alpha 1, function of alpha 2 dot 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 function of alpha n. If here alpha 1 we get image is F alpha 1, that means F alpha 1, F alpha 2 dot 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 F alpha n all are elements of V. Now let A1 F alpha 1 plus A2 F alpha 2 plus dot 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 An F alpha n equal to 0 prime, means 0 vector of V. Since F is an isomorphism, therefore we may write this as F A1 alpha 1, this F A2 alpha 2, and this F An alpha n. And again we may write for the property of isomorphic mapping, means a linear transformation. That means this F A1 alpha 1 plus A2 alpha 2 plus dot 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 An alpha n, and this equal to 0 vector of V 0 prime, since we know that F0 equal to 0 prime. Since F is isomorphic mapping, therefore F is 1 1, and for 1 1 property A1 alpha 1 plus A2 alpha 2 plus dot 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 An alpha n equal to 0, 0 vector of U. Since alpha 1 alpha 2 dot 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 alpha n all are linearly independent vectors, therefore A1 equal to 0, A2 equal to 0 dot 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 An equal to 0. So from here and here we get F alpha 1, F alpha 2, F alpha n are linearly independent vectors of V. That is, S prime is a linearly independent subset of V. Since F is an isomorphic mapping, therefore F is 1 1, F is on 2, and F is a linear transformation. Here, since F is on 2, therefore any element beta belongs to Vf, there exists an element alpha which is pre-image of beta, and we may write F alpha equal to beta. Therefore beta equal to, we may write alpha, since alpha belongs to U. So we may write alpha as a linear combination of elements of basis of U, that is A1 alpha 1 plus A2 alpha 2 plus dot 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 An alpha n equal to alpha. Since F is a linear transformation, therefore we may write this A1 F alpha 1 plus A2 F alpha 2 plus dot 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 An F alpha n. That is, any element beta belongs to Vf is a linear combination of elements of S prime. Here F alpha 1, F alpha 2 dot 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 F alpha n are elements of S prime. Therefore, linear span S prime equal to V. That is, V is generated by S prime. Since we have seen that S prime is a linearly independent subset of V, and here we see that V is generated by S prime. Therefore, S prime is a basis of V. Since S prime contains n number of elements, therefore dimension V equal to n. Dimension U is n and dimension U equal to dimension V. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.